Think about the oldest photograph you've ever seen, perhaps a faded image of ancestors you've never met, their faces frozen in a moment that feels impossibly distant. Now, shift your gaze to the night sky. The light you see from stars and galaxies isn't just a fleeting glow, it's a snapshot of the universe's distant past. Some of that light has traveled for billions of years, carrying stories from a time when galaxies were just beginning to form, and the cosmos was a vastly different place. This is the magic of cosmic time travel, where light becomes our time machine, revealing secrets from the universe's earliest days. In this video, we'll explore how scientists decode this ancient light to uncover the untold history of the cosmos. From the echoes of the Big Bang to the birth of galaxies, we'll piece together the universe's story, one photon at a time. Get ready to see the night sky in a whole new way, not just as a canvas of stars, but as a portal to the past. Light is far more than the glow that brightens our days or the shimmer that dances across the night sky. It's a cosmic messenger, a key that unlocks the secrets of the universe. Think about it. Every time you look up at the stars, you're not just seeing points of light, you're peering into the past. That's because light, as fast as it moves, traveling at an incredible 300,000 kilometers per second, still takes time to cross the immense distances of space. When you gaze at a star 100 light-years away, you're seeing it as it was a century ago. And when telescopes capture light from galaxies billions of light-years distant, they're revealing snapshots of the cosmos as it existed billions of years in the past. Light, in this way, is the ultimate time traveler, carrying stories from ancient epochs directly to us. But how does light manage to tell us so much about the universe? It's not just about brightness or color. Light carries a wealth of information encoded in its properties. Take its wavelength, for example. The wavelength of light determines its color, from the deep reds of cooler stars to the brilliant blues of hotter ones. By analyzing these wavelengths, scientists can determine the temperature of a star or the composition of a distant planet's atmosphere. Then there's intensity, the amount of light reaching us, which can reveal how massive a star is or how far away a galaxy lies. And perhaps most fascinating of all are spectral lines, the unique fingerprints of elements like hydrogen, helium, and oxygen. These lines appear as dark or bright bands in a spectrum, and they tell us exactly what a celestial object is made of. This ability of light to encode information makes it an indispensable tool for astronomers. It's like having a cosmic Rosetta Stone, translating the language of the universe into something we can understand. Through light, we can map the motion of galaxies, detect the presence of black holes, and even trace the history of the cosmos itself. Every photon that reaches us is a piece of a puzzle, a fragment of the story of how the universe began, evolved, and continues to change. So the next time you look up at the night sky, remember, the light you see isn't just illuminating the present, it's carrying whispers from the distant past, waiting to be decoded. Picture this, a universe so young, so unimaginably hot and dense, that light itself was trapped in a chaotic dance of particles and energy. This was the universe just moments after the Big Bang, an event that birthed everything we know roughly 13.8 billion years ago. In those first few seconds, the cosmos was a swirling, opaque soup of protons, electrons, and photons, so dense that light couldn't break free. It was a time when the universe was too hot and too crowded for light to travel even the tiniest distance without colliding with something else. But as the universe expanded, it began to cool, and around 380,000 years after the Big Bang, something extraordinary happened. The temperature dropped enough for electrons and protons to combine, forming neutral atoms. This monumental shift allowed light, which had been trapped for eons, to finally travel freely. The universe, once shrouded in darkness, began to glow. This glow is what we now call the cosmic microwave background, or CMB. Think of the CMB as a cosmic baby picture, a snapshot of the universe when it was just a fraction of its current age. It's not just any light, it's the oldest light we can observe, a faint whisper from the dawn of time itself. Stretching across the entire sky, this ancient light carries with it the secrets of the universe's infancy, etched into its subtle patterns and temperature variations. The discovery of the CMB in the 1960s was a game-changer for cosmology. Scientists Arno Penzias and Robert Wilson stumbled upon this faint, persistent microwave signal while working with a radio antenna. At first, they thought it was interference, maybe a faulty instrument or even pigeon droppings, but after ruling out every possible explanation, they realized they had found something far more profound, the afterglow of the Big Bang itself. What makes the CMB so significant? It's not just a relic of the past, it's a cornerstone of modern cosmology. The uniformity of the CMB's temperature, with its tiny fluctuations, provides compelling evidence for the Big Bang theory. These fluctuations are like cosmic fingerprints, revealing the seeds of galaxy clusters and the large-scale structure of the universe we see today. Without the CMB, our understanding of the universe's origins would be missing a crucial piece of the puzzle. So, the next time you look up at the night sky, remember that you're not just seeing stars and galaxies, you're witnessing the legacy of that ancient light, a glow that has traveled across billions of years to reach us. It's a reminder that the universe has a story, and the CMB is one of its most profound chapters. The cosmic microwave background, or CMB, is often described as the universe's baby picture, a snapshot of its earliest moments, frozen in time. But this isn't just any photograph. It's a map of tiny temperature differences, ripples of heat and cold that hold clues to how everything we see today came to be. These fluctuations, no larger than a few millionths of a degree, might seem insignificant at first glance, but they are the fingerprints of the universe's infancy. Each slight variation in temperature corresponds to regions of slightly higher or lower density, the seeds that would one day grow into galaxies, stars, and even us. To unravel these mysteries, scientists rely on tools that are nothing short of extraordinary. Satellites like the Planck mission have been instrumental in capturing the most detailed images of the CMB to date. Picture this, a spacecraft orbiting 1,000,000 miles from Earth, equipped with instruments so sensitive they can detect the faintest whispers of heat left over from the Big Bang. Planck's observations have given us a treasure trove of data, revealing patterns in the CMB with unprecedented precision. These patterns aren't random, they're a cosmic code, a language that tells the story of the universe's first moments. What do these patterns reveal? For one, they confirm that the early universe was not perfectly uniform. Those tiny fluctuations in density were the building blocks of everything we see today. Over billions of years, gravity amplified these differences, pulling matter together to form the vast cosmic web of galaxies and galaxy clusters that stretch across the cosmos. But the CMB doesn't just tell us about structure, it also holds clues about the universe's composition. By analyzing the patterns, scientists have been able to determine that ordinary matter, the stuff that makes up stars, planets, and people, accounts for only about 5% of the universe. The rest, dark matter and dark energy, two of the most mysterious and elusive components of our cosmos. The Planck mission's findings have also provided crucial support for the Big Bang theory. giving us a clearer picture of how the universe expanded and cooled in its earliest moments. It's like piecing together a puzzle with pieces scattered across billions of light years, and as we decode more of these cosmic clues, we're not just learning about the universe's past, we're uncovering insights that could shape our understanding of its future. The CMB is more than a relic, it's a roadmap guiding us through the vast and intricate history of everything that exists. Imagine holding a flashlight in a dark room. The light beams out in a straight line, crisp and clear, but what if the room itself was stretching, pulling the beam with it? The light would stretch too, its waves elongating as the distance grows. This is essentially what happens to light as it travels across the expanding universe. The light waves stretch, shifting their color toward the red end of the spectrum, a process called redshift. The farther the light travels, the more it stretches and the redder it appears. This isn't just a quirk of physics, it's a cosmic time machine. By measuring redshift, astronomers can determine how far away an object is and, in turn, how long its light has been traveling to reach us. The greater the redshift, the older the light, and the deeper we're peering into the universe's past. To measure redshift, scientists analyze the light from distant galaxies or stars using spectrometers, instruments that break light into its component colors. Each element in the universe, like hydrogen or helium, leaves a unique fingerprint in the spectrum of light. When light is redshifted, these fingerprints shift toward longer wavelengths, like a song played in slow motion. By comparing the shifted fingerprints to their known positions, astronomers can calculate how much the light has stretched and, consequently, how far it's traveled. This method has allowed us to map the universe's expansion and even estimate its age, revealing that the light we see from some of the most distant galaxies has been journeying toward us for over 13 billion years. But redshift isn't just a measuring stick for distance, it's a window into the universe's history. By studying the redshift of galaxies, we can trace how the universe has evolved over time, uncovering clues about the formation of galaxies, the distribution of dark matter, and even the mysterious force driving cosmic expansion. It's like reading the universe's diary, written in the language of light, and as our telescopes grow more powerful, the stories we uncover through redshift will only grow richer, offering glimpses of a cosmos that's far older and more dynamic than we ever imagined. Galaxies are like the cities of the cosmos, vast, intricate, and teeming with activity. But how did these cosmic metropolises come to be? The answer lies in the ancient light that has traveled across the universe for billions of years, carrying with it the secrets of their birth and growth. When we look at distant galaxies, we're not just seeing stars and gas, we're peering back in time, witnessing snapshots of the universe in its youth. This light is a time capsule, revealing the conditions under which galaxies first emerged and how they've evolved over eons. Take, for example, the faint glow of a galaxy billions of light years away. As its light reaches us, it tells a story. The colors, the intensity, and even the way the light is stretched by the expansion of the universe. All of these clues help astronomers decode the galaxy's composition, its rate of star formation, and how it interacts with its cosmic neighbors. It's like reading a history book written in photons, each page detailing a different chapter in the galaxy's life. But galaxies didn't form in isolation. They're part of a much larger structure known as the cosmic web, an immense network of dark matter and gas that stretches across the universe. Dark matter, though invisible, plays a crucial role in this story. Its gravitational pull acts as the scaffolding, drawing gas and dust together to form the first galaxies. Over time, these galaxies grew, collided, and merged, creating the diverse array of shapes and sizes we see today. Ancient light allows us to trace this process, showing us how galaxies evolved from faint, clumpy structures into the majestic spirals and ellipticals we observe now. By studying this light, we're not just learning about galaxies, we're uncovering the history of the universe itself. It's a story of gravity, dark matter, and the tenacity of light to travel across unimaginable distances to reach us. And with every new observation, we add another piece to the puzzle, bringing us closer to understanding how the cosmos came to be the way it is. Picture this, a light so intense it outshines entire galaxies, blazing across the cosmos from a time when the universe was still in its teenage years. These are quasars, cosmic beacons that serve as time capsules from the early universe. At their core lies a supermassive black hole, millions or even billions of times more massive than our Sun, devouring matter at an astonishing rate. As gas and dust spiral into these black holes, they heat up to extreme temperatures, releasing energy that makes quasars the brightest objects in the known universe. What makes quasars truly remarkable is their distance. The light we see from them today began its journey billions of years ago, meaning we're peering back in time to an era when galaxies were still forming and the universe was a far more chaotic place. By studying this ancient light, astronomers can piece together the story of how the universe evolved. For instance, quasars reveal the presence of heavy elements like carbon and oxygen in the early universe, long before stars had time to forge them in their cores. This suggests that even in its youth, the cosmos was already bustling with activity, seeding the building blocks of future stars, planets, and even life. But how do we study these distant powerhouses? Telescopes, both on Earth and in space, are our primary tools. Instruments like the Hubble Space Telescope and the James Webb Space Telescope capture the faint light from quasars, allowing scientists to analyze their spectra, the unique fingerprint of light that reveals their composition, temperature, and motion. This data helps us understand not just the quasars themselves, but also the environment around them, such as the gas and dust that filled the early universe. Quasars also offer clues about the growth of supermassive black holes. These cosmic giants didn't start out so massive, they grew over time, and quasars give us a front-row seat to this process. By observing how quasars evolve, we can trace the history of black holes and their role in shaping galaxies. It's a reminder that even the most mysterious and powerful forces in the universe are part of an ongoing story, one that began billions of years ago and continues to unfold today. Imagine witnessing a star's final act, a brilliant explosion so powerful it outshines billions of stars combined. This is a supernova, the dramatic end of a massive star's life. These cosmic events aren't just spectacular to observe, they're also invaluable tools for unraveling the mysteries of the universe. When a supernova occurs, it releases an immense burst of light that can be seen across billions of light years, carrying with it a wealth of information about the cosmos. One of the most fascinating aspects of supernova is how they serve as cosmic mile markers. Scientists use a specific type of supernova, called type Ia, as a standard candle to measure distances in the universe. These supernovae explode with such a predictable brightness that by comparing their apparent brightness from Earth to their known intrinsic brightness, astronomers can calculate how far away they are. This technique has played a key role in one of the most groundbreaking discoveries in modern cosmology, the accelerating expansion of the universe. But what's driving this acceleration? That's where dark energy comes into the picture. Supernovae provide critical clues about this mysterious force, which makes up nearly 70% of the universe's energy. By studying the light from ancient supernovae, scientists found that the universe isn't just expanding, it's doing so at an ever-increasing rate. This discovery, which earned the Nobel Prize in Physics in 2011, has reshaped our understanding of the cosmos and raised new questions about its ultimate fate. Supernovae also act as cosmic time capsules. The light from these explosions travels through space for millions or even billions of years before reaching us, allowing us to peer back in time and observe the universe as it was long ago. Each flash of light carries a snapshot of the conditions in the early universe, offering a glimpse into the past and helping us piece together the story of how the cosmos evolved. From measuring the universe's expansion to shedding light on dark energy, supernovae are more than just fleeting moments of cosmic brilliance. They're essential tools for exploring the history and future of the universe. Every explosion tells a story, and by listening to these celestial echoes, we're uncovering secrets that stretch across space and time. In 1995, the Hubble Space Telescope did something extraordinary. It turned its gaze toward what appeared to be nothing more than a dark, empty patch of sky. For 10 consecutive days, it collected light from this seemingly barren region, and when the data was processed, the result was nothing short of breathtaking. The Hubble Deep Field image revealed thousands of galaxies, each one a swirling island of stars, dust, and gas, stretching back billions of years into the universe's past. This wasn't just a photograph, it was a portal into the cosmos's history, a snapshot of time itself. What made this image so groundbreaking was its ability to show us galaxies as they existed when the universe was still young, some of them dating back to when the cosmos was just 5% of its current age. Think about that for a moment. We're not just seeing distant objects, we're peering back in time, witnessing the universe in its infancy. This single image shattered our assumptions about the vastness of space and the sheer number of galaxies that fill it. It showed us that even the emptiest corners of the sky are teeming with cosmic activity, waiting to be discovered. But how did Hubble achieve this remarkable feat? The secret lies in its ability to collect faint light over long periods. By focusing on one spot for days, the telescope gathered enough photons to reveal objects that are otherwise invisible to us. It's like using a long-exposure camera to capture the faint glow of stars in a dark night sky. The result is a picture that not only shows galaxies in incredible detail, but also highlights their incredible diversity. Some are spiral galaxies with their elegant, swirling arms, while others are elliptical, smooth, and featureless. There are even irregular galaxies, chaotic and unstructured, each one telling a unique story about the universe's evolution. The Hubble Deep Field didn't just expand our knowledge of the cosmos, it fundamentally changed how we see our place within it. Before this image, we had no idea just how many galaxies existed or how far back in time we could observe. Now, we know that the universe is filled with billions upon billions of galaxies, each one a potential home for planets, stars, and maybe even life. It's a humbling reminder of just how vast and interconnected the cosmos truly is. And it all started with a decision to point a telescope at what seemed to be nothing at all. Gravity doesn't just pull objects toward each other, it can also bend the very fabric of space and time, and in doing so, it bends light itself. This astonishing effect is called gravitational lensing, and it's one of the most powerful tools astronomers have to explore the cosmos. Imagine a massive object, like a galaxy or a cluster of galaxies, sitting between us and a distant light source. The immense gravity of that object warps the space around it, curving the path of light traveling from the distant source. The result, a cosmic magnifying glass that can amplify and sometimes even distort the light, bringing faraway objects into view that would otherwise be invisible to us. Gravitational lensing was first predicted by Albert Einstein's theory of general relativity over a century ago. He theorized that massive objects could bend light, but it wasn't until the late 1970s that astronomers observed this phenomenon in action. The discovery was groundbreaking. It confirmed Einstein's predictions and opened up a whole new way to study the universe. Today, gravitational lensing is used to peer into the most distant reaches of space, capturing light from galaxies and quasars that formed billions of years ago when the universe was still in its infancy. But how does it work? Picture a magnifying glass sitting on a table. When you hold it over a small object, the glass bends the light, making the object appear larger and clearer. Gravitational lensing does something similar, but on a cosmic scale. A massive object in space, like a galaxy cluster, acts as the lens. Light from a distant object, perhaps a galaxy billions of light years away, passes through this lens. The gravity of the cluster bends the light, focusing it and making the distant galaxy appear brighter, and sometimes even creating multiple images of the same object. These distorted or multiplied images are like cosmic echoes, giving us a glimpse into the universe's past. One of the most fascinating aspects of gravitational lensing is its ability to reveal dark matter. Since dark matter doesn't emit light, it's invisible to traditional telescopes, but because dark matter has mass, it interacts with gravity. When light from a distant object passes through a region rich in dark matter, the lensing effect can reveal the presence of this mysterious substance. It's like seeing the shadow of something we can't directly observe, a clue to one of the universe's greatest mysteries. Gravitational lensing has also allowed astronomers to study the earliest moments of cosmic history. By observing lensed galaxies and quasars, scientists can measure the expansion rate of the universe, map the distribution of dark matter, and even test the fundamental laws of physics. It's as if the universe itself has handed us a tool to look back in time, revealing the untold stories of ancient light that has traveled across the cosmos for billions of years. Imagine an invisible force, one you can't see, touch, or measure directly, yet it shapes everything around you on a cosmic scale. This is dark matter, a mysterious substance that makes up roughly 27% of the universe. Unlike stars, planets, or even gas clouds, dark matter doesn't emit, absorb, or reflect light. It's entirely invisible to our telescopes, but just because we can't see it doesn't mean it isn't there. In fact, its presence is felt everywhere, woven into the very fabric of the cosmos. How do we know dark matter exists if it's invisible? The answer lies in its gravitational influence. Think of it like this: when you see leaves swirling in the wind, you can't see the air moving them, but you know it's there because of its effects. Dark matter works similarly. Its gravity tugs on galaxies, bending their paths and shaping how they move through space. Without dark matter, galaxies would fly apart, and the universe as we know it wouldn't exist. But here's where ancient light comes in. The oldest light in the universe, known as the cosmic microwave background, holds clues about dark matter. This faint glow, left over from the Big Bang, carries tiny ripples, imprints of the early universe's structure. These ripples reveal how matter, including dark matter, was distributed billions of years ago. By studying this ancient light, scientists can map the invisible scaffolding of dark matter that underlies the cosmos. It's like using a cosmic fingerprint to uncover the hidden architect of the universe. dark matter doesn't just shape galaxies, it dictates the large-scale structure of the universe itself. Vast networks of galaxies, connected by filaments of dark matter, form a cosmic web stretching across billions of light years. Without this invisible framework, the universe would look entirely different. And while we still don't know exactly what dark matter is made of, its gravitational fingerprints are everywhere, from the motion of stars within galaxies to the bending of light around massive galaxy clusters. So, as we peer deeper into the cosmos, ancient light continues to guide us, revealing the unseen forces that have shaped the universe since its birth. Dark matter may remain elusive, but its influence is undeniable, reminding us that the universe is far more complex and more mysterious than it appears. Imagine a force so powerful that it can stretch the fabric of the universe itself, pushing galaxies apart faster than the speed of light. This isn't science fiction, it's dark energy, one of the greatest mysteries in modern cosmology. Unlike gravity, which pulls things together, dark energy seems to do the opposite, acting as a kind of cosmic repellent that accelerates the expansion of the universe. But here's the twist: we don't actually know what it is. We can't see it, touch it, or directly measure it. Yet its fingerprints are everywhere, etched into the light of ancient supernovae and woven into the very structure of the cosmos. To understand how we discovered dark energy, we need to look back at the light from exploding stars billions of years ago. Astronomers observed that distant supernova explosions marking the death of massive stars were dimmer than expected. This dimness wasn't due to dust or distance alone. Instead, it suggested that the universe was expanding faster than anyone had predicted. Something was counteracting gravity's pull, pushing galaxies apart with increasing speed. That something is what we now call dark energy. But how does ancient light help us uncover this mystery? When light travels across the universe, it carries with it clues about the space it has traversed. By studying the brightness and redshift of distant supernovae, scientists can map how the universe has expanded over time. These observations reveal a startling truth. Around 5 billion years ago, the universe's expansion began to accelerate. This acceleration aligns with the presence of dark energy, a force that now makes up roughly 70% of the universe's total energy. What's truly fascinating is how dark energy shapes the future of the cosmos. If it continues to dominate, the universe could face a cold, lonely fate, where galaxies drift so far apart that they become invisible to one another. But there's still so much we don't know. Is dark energy constant, or does it change over time? Could it one day reverse its effect, pulling the universe back together? These questions remain unanswered, but every piece of ancient light we study brings us closer to unraveling the secrets of this cosmic enigma. Before galaxies painted the cosmos with their swirling arms of starlight, the universe was a very different place. Picture a vast, silent expanse, no planets, no galaxies, just an endless sea of hydrogen and helium gas, cloaked in darkness. This era, known as the Dark Ages, was a time before light had truly begun to shine. But then, something extraordinary happened. The first stars, called Population 3 stars, burst into existence, igniting what we now call the cosmic dawn. These stars weren't like the ones we see today. They were massive, burning hot, and short-lived, but their birth marked the end of the universe's dark, formless phase. What makes these ancient stars so fascinating is that they were the universe's first factories. Inside their cores, they forged heavier elements like carbon, oxygen, and nitrogen, ingredients essential for life as we know it. When these stars died, often in colossal explosions, they scattered these elements into space, seeding the cosmos with the raw materials for future stars, planets, and even us. But here's the challenge. These population 3 stars are incredibly elusive. They burned bright and fast, billions of years ago, and their light is now so faint and distant that detecting them is like searching for a single candle in a galaxy filled with fireworks. Yet, their faint glow carries priceless information about the universe's early chemistry and how the first structures like galaxies began to form. Scientists are piecing together clues using some of the most advanced telescopes ever built, like the James Webb Space Telescope, which is designed to peer into the farthest reaches of space and time. By studying the light from these ancient stars, we're not just looking back at the universe's infancy, we're uncovering the story of our own origins. Every atom in our bodies, every star in the night sky, traces back to these first, pioneering stars. They didn't just light up the cosmos, they set the stage for everything that came after. Imagine a universe cloaked in darkness, where the first stars have just ignited, casting their faint glow into the void. These early stars were no ordinary beacons, they were cosmic powerhouses, emitting intense radiation that began to reshape the very fabric of the universe. This transformative period, known as reionization, marked a monumental shift in cosmic history. For hundreds of millions of years, the universe had been shrouded in a dense fog of neutral hydrogen gas, absorbing light and keeping the cosmos in shadow. But as these first stars and galaxies burned brighter, their radiation began to ionize the hydrogen, stripping electrons from atoms and turning the fog into a sea of charged particles. This process wasn't instantaneous. It unfolded over hundreds of millions of years, gradually clearing the way for light to travel freely across vast distances. Reionization was like a cosmic sunrise, illuminating the universe and setting the stage for the transparent cosmos we see today. But how do we study such a distant epoch? The answer lies in ancient light. The faint echoes of this era are imprinted in the cosmic microwave background, the afterglow of the Big Bang, and in the light from some of the most distant galaxies ever observed. By analyzing these signals, scientists can piece together the timeline of reionization and understand its profound impact on the universe's evolution. Reionization didn't just clear the cosmic fog, it also influenced the formation of galaxies and large-scale structures. As light began to travel freely, it carried energy across the universe, heating the gas between galaxies and shaping the conditions for future star formation. This epoch was a turning point, a moment when the universe transitioned from a dark, murky expanse to a luminous, interconnected web of galaxies. And while the process itself happened billions of years ago, its effects are still visible today, etched into the very fabric of the cosmos. Through the study of reionization, we gain a deeper understanding of how the universe grew from a sea of darkness into the vibrant, light-filled expanse we now call home. The James Webb Space Telescope, launched in 2021, has opened a new window into the cosmos, allowing us to witness the universe as it was billions of years ago. Unlike its predecessor, the Hubble Space Telescope, which primarily captured visible light, JWST specializes in infrared wavelengths. This unique capability lets it cut through cosmic dust and observe the faintest glimmers of ancient light that has traveled across unimaginable distances and times to reach us. It's like holding a time machine in the palm of our hands, one that reveals the universe's earliest chapters. One of JWST's most astonishing achievements is its ability to glimpse the formation of the first galaxies. These ancient structures, born just a few 100 million years after the Big Bang, are incredibly faint and distant. Yet, JWST powerful instruments have detected their light, offering us a snapshot of a time when the universe was young and chaotic. By studying these primordial galaxies, scientists are piecing together how the first stars ignited, how galaxies assembled, and how the universe evolved from simplicity to the complexity we see today. But JWST isn't just about looking back in time. It's also reshaping our understanding of the present. Its observations of nearby star-forming regions, exoplanets, and even our own solar system have revealed details we never thought possible. For example, JWST has detected water vapor in the atmospheres of distant planets, hinting at the potential for life beyond Earth. It's also provided unprecedented views of celestial phenomena like dying stars and swirling nebulae, painting a richer picture of the cosmos we inhabit. What makes JWST truly groundbreaking is how it bridges the gap between the ancient and the modern. By studying the faint whispers of light from the early universe and combining that with its observations of more recent cosmic events, it's helping us weave a more complete story of existence. Each discovery adds another thread to the tapestry, revealing patterns and connections that were once hidden. Through JWST, we're not just observers of the universe, we're becoming its storytellers, uncovering secrets that have waited billions of years to be told. In the very first moments after the Big Bang, something extraordinary happened, something so rapid and dramatic that it shaped the entire universe as we know it. This event is called cosmic inflation, and it's one of the most fascinating ideas in modern cosmology. Picture this: in less than a blink of an eye, the universe expanded exponentially, stretching from a size smaller than an atom to something far larger than our entire observable cosmos today. This wasn't just a gradual expansion, it was a sudden, explosive growth spurt that set the stage for everything that followed. But how do we know this actually happened? One of the key pieces of evidence comes from ancient light, specifically the cosmic microwave background, or CMB. This faint glow, left over from the early universe, is like a snapshot of the cosmos when it was just 380,000 years old. The CMB reveals tiny fluctuations in temperature, subtle ripples that tell us something profound. The universe was incredibly uniform on a large scale, but with just enough variation to allow galaxies, stars, and planets to form later on. These ripples, incredibly consistent across the sky, are exactly what cosmic inflation predicts. Think of it like baking bread. If you start with a lump of dough and roll it out smoothly, tiny imperfections, little air pockets or uneven spots, get stretched out as the dough expands. Inflation works the same way. Before inflation, quantum fluctuations, tiny, random variations in energy existed on a microscopic scale. But as the universe rapidly expanded, these fluctuations were stretched out, becoming the seeds for the large-scale structures we see today. Without inflation, the universe might have been far more chaotic, and we might not be here to observe it. The implications of cosmic inflation are staggering. It doesn't just explain why the universe looks the way it does, it also hints at something even more profound: the possibility of a multiverse. If inflation happened once, it could have happened elsewhere, creating other universes with entirely different properties. This idea pushes the boundaries of our understanding, challenging us to think bigger than ever before. And yet, it all comes back to that ancient light, a faint echo from the dawn of time, whispering secrets about how everything began. What if everything we see, the stars, the galaxies, the vast expanse of space, is just a tiny fraction of something much, much bigger? The multiverse hypothesis challenges us to think beyond the boundaries of our observable universe, proposing that ours might be just one of countless others, each with its own unique set of physical laws. It's a mind-bending idea, but one that's deeply rooted in the science of cosmic inflation and the ancient light that still whispers secrets from the dawn of time. When we look at the cosmic microwave background radiation, that faint glow left over from the Big Bang, we're essentially staring at a snapshot of the universe when it was just a few 100,000 years old. This ancient light carries patterns, tiny fluctuations in temperature that hint at the early seeds of galaxies, but some scientists believe these patterns might also hold clues to something even more profound: the possibility that our universe isn't alone. According to cosmic inflation theory, the rapid expansion of the universe in its earliest moments may have created bubbles of space-time, each one potentially giving rise to its own universe. These bubbles could exist alongside ours, forever out of reach yet governed by entirely different rules of physics. Imagine, for a moment, a universe where gravity is stronger, where stars burn brighter and faster, or where the very concept of time works differently. These aren't just science fiction scenarios, they're possibilities within the multiverse framework, and while we can't directly observe these other universes, the patterns in the cosmic microwave background might offer indirect evidence. Some researchers suggest that anomalies in this ancient light, areas where the temperature fluctuations don't quite match our expectations, could be signatures of collisions between our universe and a neighboring one. But what does this mean for our understanding of reality? If the multiverse exists, it could fundamentally change how we see ourselves and our place in the cosmos. Instead of being the only universe, we might be part of an infinite tapestry of realities, each one a unique experiment in physics. It's a humbling thought, and one that raises as many questions as it answers. Could life exist in these other universes? What would it look like under different physical laws? And how might the multiverse reshape our search for a unified theory of everything? As we continue to study the ancient light of the cosmos, the answers to these questions remain tantalizingly out of reach, but the journey to uncover them is just as thrilling as the possibilities themselves. Every observation, every theory, brings us closer to understanding not just our universe, but the potential existence of countless others. And in that journey, we're reminded that the cosmos is far stranger and far more wondrous than we ever imagined. What does the future hold for the cosmos? Will it stretch endlessly into a cold, lifeless void, or will it collapse back in on itself in a fiery finale? These are the questions that haunt astronomers and cosmologists as they peer into the ancient light of the universe. The clues to the universe's ultimate fate are hidden in the very fabric of space and time, waiting to be decoded. And one of the most critical pieces of this cosmic puzzle is dark energy, the mysterious force driving the universe's expansion. Imagine the universe as a vast, stretching canvas. Every galaxy, every star, every speck of dust is moving away from everything else, carried by the relentless push of dark energy. This expansion isn't slowing down, it's speeding up. But what does this mean for the future? If dark energy continues to dominate, the universe might face what scientists call the heat death. In this scenario, galaxies will drift so far apart that the night sky will grow darker and darker. Stars will burn out, and even the remnants of matter will decay into a cold, lifeless expanse. It's a chilling thought, but one supported by the way ancient light, the cosmic microwave background, reveals the universe's accelerating expansion. But there's another possibility, the Big Crunch. What if dark energy weakens over time, or gravity gains the upper hand? In this scenario, the universe's expansion could slow, stop, and then reverse. Galaxies would hurtle back toward each other, space itself would shrink, and everything would collapse into a single, unimaginably dense point, a cosmic mirror of the Big Bang. Some theories even suggest that this could trigger a new Big Bang, restarting the cycle of creation. The ancient light we observe today holds subtle hints about whether this fate is possible, from the distribution of galaxies to the way gravity bends light across the cosmos. So, which path is the universe on? The answer lies in the delicate balance between dark energy and gravity, a tug of war that's been playing out since the dawn of time. Ancient light, captured by telescopes and analyzed by scientists, helps us weigh these forces and predict the universe's trajectory. It's like reading a cosmic clock, ticking toward an uncertain future. And while we can't yet say for certain which fate awaits us, one thing is clear: the universe's story is far from over. Every discovery brings us closer to understanding not just where we came from, but where we're headed. Black holes are often imagined as cosmic vacuum cleaners, devouring everything in their path. But they're far more than that. They're also incredible time capsules, offering us a glimpse into the universe's distant past. When matter spirals into a black hole, it doesn't just vanish without a trace. Instead, it releases intense radiation, including light, as it's pulled toward the event horizon. This light carries with it vital clues about the environment and conditions of the early universe. By studying this radiation, scientists can piece together a timeline of cosmic events, almost like reading a history book written in the language of light. What makes black holes so unique is their ability to warp spacetime itself. Their immense gravitational pull doesn't just trap matter, it also bends and stretches the light that escapes from their vicinity. This phenomenon, known as gravitational lensing, allows astronomers to observe light that has traveled for billions of years, giving us a direct view into the universe's younger days. It's as if black holes act as cosmic magnifying glasses, amplifying the faint signals from galaxies and stars that existed long before our own solar system formed. But how does this help us understand the early universe? The answer lies in the way black holes interact with their surroundings. As matter falls into a black hole, it heats up and emits X-rays and other forms of high-energy radiation. These emissions carry information about the composition and temperature of the material, offering a snapshot of the universe at that moment in time. By analyzing this data, researchers can reconstruct the conditions of the cosmos billions of years ago, shedding light on how galaxies formed, how stars were born, and even how the first structures in the universe took shape. In a way, black holes are like cosmic detectives, preserving evidence from the universe's infancy. They don't just help us understand the past, they also challenge our understanding of fundamental physics. For example, the way black holes distort light and time provides a testing ground for Einstein's theory of general relativity, pushing the boundaries of what we know about the nature of spacetime itself. By studying these enigmatic objects, we're not just looking back in time, we're also uncovering the rules that govern the fabric of reality. Neutrinos are often called the universe's ghostly messengers, and for good reason. These nearly massless particles zip through space, and even through entire planets without slowing down or leaving much of a trace. They're so elusive that trillions of them pass through your body every second, yet you'd never know it. What makes them truly fascinating, though, is the story they carry. Neutrinos were born in the fiery aftermath of the Big Bang, and they've been traveling across the cosmos ever since, holding secrets about the universe's earliest moments that even light can't reveal. Unlike photons, which make up the ancient light we see as the cosmic microwave background, neutrinos rarely interact with matter. This makes them incredibly challenging to detect, but it also means they've been largely untouched since their creation. While light can be absorbed, scattered, or blocked by cosmic dust and gas, neutrinos travel unimpeded, offering a pristine snapshot of the universe just seconds after it began. They're like cosmic time capsules, preserving details about the conditions and forces at play during the universe's infancy. But capturing these ghostly particles is no small feat. Detecting neutrinos requires incredibly sensitive equipment, often buried deep underground to shield against interference from other particles. Experiments like the Ice Cube Neutrino Observatory in Antarctica use massive arrays of sensors embedded in ice to catch the rare flashes of light produced when a neutrino finally interacts with matter. Even then, the data is sparse and requires painstaking analysis. Yet, every detection brings us closer to understanding the universe's most fundamental processes, from the behavior of supernovae to the mysterious imbalance between matter and antimatter. What's truly remarkable is how neutrinos complement the story told by ancient light. While the cosmic microwave background gives us a picture of the universe hundreds of thousands of years after the Big Bang, neutrinos take us back even further, to the very first moments of existence. Together, these two messengers weave a richer tapestry of cosmic history, filling in gaps that neither could address alone. It's a bit like piecing together a puzzle where each piece reveals a different part of the picture. One shows the colors, the other the shapes, and together they create a complete image. Studying neutrinos isn't just about looking back in time. It's also about understanding the universe's most enigmatic forces. Their tiny but non-zero mass hints at physics beyond the standard model, the framework that explains the fundamental particles and forces we know. Every neutrino detected could hold clues to questions we haven't even thought to ask yet. And as our detection methods improve, we're inching closer to unlocking these cosmic secrets, one ghostly particle at a time. In 2015, a groundbreaking discovery shook the foundations of astrophysics. For the first time, scientists detected gravitational waves, ripples in the very fabric of spacetime itself. This monumental achievement confirmed a prediction made by Albert Einstein a century earlier in his theory of general relativity. Imagine spacetime as a vast, invisible ocean. When massive objects like black holes or neutron stars collide, they send out waves, much like a stone creating ripples in water. These waves carry secrets about some of the most violent and energetic events in the cosmos. Gravitational waves are more than just cosmic curiosities, they're messengers. Unlike light, which can be blocked or distorted by dust and gas, these waves travel unimpeded, bringing us direct information about their origins. When two black holes spiral into each other, merging into one, they release energy in the form of gravitational waves that ripple across the universe. These waves allow us to listen to events we could never see, like the collision of neutron stars or the birth of supermassive black holes. It's as if the universe has handed us a new set of ears to complement our telescopes. What makes this discovery so transformative is how it complements what we already know from studying ancient light. For centuries, astronomers have relied on light, visible, infrared, X-rays, and more, to peer into the universe's past. But light can only tell us part of the story. Gravitational waves open up a new dimension of exploration, revealing details about the objects that produce them, like their masses, spins, and distances. Together, light and gravitational waves form a powerful duo, giving us a more complete picture of the cosmos. This discovery didn't just confirm Einstein's theory, it revolutionized how we study the universe. By combining observations of ancient light with the detection of gravitational waves, scientists are piecing together the history of the universe in ways that were once unimaginable. From the violent collisions of black holes to the faint echoes of the Big Bang itself, these ripples in spacetime are helping us uncover the untold stories of our cosmic past. What if the key to finding life beyond Earth has been traveling through space for billions of years, hidden in the faint glow of ancient starlight? This isn't science fiction, it's the cutting edge of astronomy. When light from distant stars passes through the atmospheres of exoplanets, it carries with it a chemical fingerprint. By analyzing this light, scientists can hunt for biosignatures, the telltale signs of life. These are molecules like oxygen, methane, or even more complex compounds that, under the right conditions, could hint at biological activity. But how does this work in practice? Imagine a planet orbiting a star trillions of miles away. As light from that star travels through the planet's atmosphere, certain wavelengths are absorbed by gases present there. When astronomers capture this light using powerful telescopes like the James Webb Space Telescope, they can decode these absorption patterns to determine what gases are present. If they find a mix of gases that can't easily be explained by non-biological processes like oxygen and methane coexisting in the same atmosphere, it could be a strong indicator of life. Detecting these biosignatures isn't simple, though. Space is vast, and the signals we're searching for are incredibly faint. The light we're analyzing has traveled for millions or even billions of years, and by the time it reaches us, it's been stretched and distorted by the expansion of the universe. On top of that, some biosignatures can be produced by natural processes that don't involve life at all. For example, methane can be released by volcanic activity, and oxygen can accumulate through the breakdown of water molecules by ultraviolet light. This means scientists have to be meticulous, ruling out every possible non-biological explanation before even considering the possibility of extraterrestrial life. Still, the potential is staggering. Each new exoplanet discovered increases the odds that somewhere out there, life exists, and with every advance in telescope technology, we're getting better at sifting through the ancient light of the cosmos for clues. The search for extraterrestrial life isn't just about finding aliens, it's about understanding our place in the universe. What if the answer to one of humanity's oldest questions is written in the light of stars that burned out long before Earth even formed? Have you ever wondered why the universe seems tailor-made for life? It's as if every fundamental constant, every law of physics was calibrated just right to allow stars to shine, planets to form, and life to emerge. This idea isn't just a coincidence, it's at the heart of what scientists call the Anthropic Principle. At its core, the Anthropic Principle suggests that the universe's physical constants are finely tuned in a way that makes life possible. But how do we know this? And what does ancient light have to do with it? When we look at the cosmos, we see a delicate balance. For example, the strength of gravity, the speed of light, and even the mass of subatomic particles are set with such precision that even the tiniest change would render the universe lifeless. If gravity were slightly stronger, stars would burn out too quickly. If it were weaker, galaxies might never have formed. This fine-tuning is what makes the Anthropic Principle so fascinating. It raises profound questions about why the universe is the way it is. Ancient light, like the cosmic microwave background radiation, gives us clues about this fine-tuning. This faint glow, left over from the Big Bang, is like a snapshot of the early universe. By studying it, we can measure the universe's properties with incredible precision. What we've found is that the conditions necessary for life, things like the right balance of matter and energy, were set in place almost immediately after the universe began. It's as if the universe had a blueprint for life from the very start, but here's where things get even more intriguing. The Anthropic Principle doesn't just tell us about the universe, it also makes us reflect on our place in it. Are we here by chance, or is there something deeper at play? Some scientists argue that the fine-tuning of the universe points to the existence of a multiverse, where countless universes exist, each with different physical constants. In this view, we just happen to live in the one where conditions are right for life. Others see it as evidence of a deeper cosmic purpose. What's clear is that ancient light doesn't just illuminate the past, it helps us grapple with these big questions. By studying the universe's earliest moments, we're not just learning about how it began, but why it might be the way it is, and that brings us back to the Anthropic Principle, a reminder that the universe, in all its vastness, might just have a special place for us. Imagine trying to read a book written in a language you've never seen before. Without the right tools, the words would be meaningless. Now, think of ancient light as that book, and mathematics as the decoder that unlocks its secrets. It's not just a tool, it's the very language that allows us to translate the whispers of the cosmos into something we can understand. From the faint glow of distant galaxies to the subtle ripples in the cosmic microwave background, math is the bridge between observation and insight. One of the most powerful mathematical tools in cosmology is the redshift calculation. When light travels across the vast expanse of the universe, it stretches, shifting toward the red end of the spectrum. This phenomenon, known as redshift, is a direct result of the universe's expansion. By measuring how much the light has shifted, we can determine not only how far away a galaxy is but also how fast it's moving away from us. It's like listening to the echo of a distant drum and figuring out how far the sound has traveled. Without the precision of mathematics, this echo would remain just noise. But redshift is only the beginning. To truly grasp the story of the cosmos, we need to model its origins. This is where equations like those describing cosmic inflation come into play. Inflation theory suggests that the universe expanded exponentially in the tiniest fraction of a second after the Big Bang. Mathematical models help us simulate this rapid expansion, providing insights into how the universe grew from a microscopic point to the vast expanse we see today. These models aren't just abstract concepts, they're the blueprints that guide our understanding of the universe's infancy. And then there's the cosmic microwave background, the oldest light in the universe. This faint glow is a snapshot of the cosmos when it was just 380,000 years old. To decode this light, we rely on mathematical techniques like Fourier transforms, which break down complex signals into simpler components. It's like taking a symphony and isolating each instrument to understand how they all come together to create the music. Through math, we can peel back the layers of this ancient light, revealing the patterns and fluctuations that shaped the universe. What's truly remarkable is how these mathematical tools don't just describe the universe, they predict it. The equations that describe the behavior of light and matter have led us to discoveries we couldn't have imagined, like dark energy and dark matter. They've allowed us to peer billions of years into the past and glimpse the universe's earliest moments. Math isn't just a tool, it's the lens through which we see the cosmos in all its complexity and beauty. So, the next time you look up at the night sky, remember this: every star, every galaxy, every flicker of light has a story to tell, and it's through the language of mathematics that we're able to listen. As we journey deeper into the cosmos, it's easy to marvel at how far we've come in unraveling the universe's history. But even with the power of ancient light, there's a point where our vision begins to blur, a cosmic wall that stands between us and the very beginning. This invisible barrier isn't made of stone or metal, but something far more mysterious, a dense, opaque plasma that filled the early universe. Picture a fog so thick that not even light could pass through it. This is what scientists call the Epoch of Recombination, a time when the universe was so hot and dense that atoms couldn't form, and light was trapped in a chaotic dance with particles. For us, this means that no matter how powerful our telescopes become, there's a limit to how far back we can see. The earliest light we can observe comes from a time about 380,000 years after the Big Bang, when the universe finally cooled enough for light to break free and travel across space. This light, known as the cosmic microwave background, is like a snapshot of the universe in its infancy, a faint, glowing echo of its fiery birth. But what lies beyond this cosmic curtain? The Big Bang itself remains hidden, shrouded in a veil of plasma and energy that even the most advanced technology can't pierce. This doesn't mean we're out of options, though. Scientists are using ingenious methods, like studying the subtle ripples in the cosmic microwave background, to piece together what might have happened in those first moments. It's a bit like trying to reconstruct a story from the faintest whispers of its opening lines. While we may never directly observe the Big Bang, every discovery brings us closer to understanding the universe's origins and reminds us that even in the face of cosmic mysteries, curiosity and ingenuity can light the way. The future of cosmic time travel is unfolding before our eyes, and it's powered by some of the most groundbreaking technologies humanity has ever developed. Picture this: next-generation telescopes, more powerful than anything we've seen before, are being designed to peer deeper into the cosmos than ever. These aren't just upgrades, they're leaps forward. For instance, the James Webb Space Telescope, already revolutionizing our view of the universe, is just the beginning. Upcoming missions like the Nancy Grace Roman Space Telescope and the extremely large telescope on Earth are set to push the boundaries even further, capturing ancient light from the earliest galaxies and giving us a clearer picture of the universe's infancy. But it's not just about bigger mirrors or sharper lenses. New detection methods are changing the game entirely. Imagine instruments that can sense the faintest whispers of light from stars that burned out billions of years ago, or tools that can analyze the subtle distortions of spacetime caused by gravitational waves. These innovations are like time machines, allowing us to reconstruct events from the distant past with astonishing precision. And let's not forget the role of artificial intelligence in sifting through the mountains of data these telescopes collect. AI is helping astronomers identify patterns and anomalies that might otherwise go unnoticed, turning what was once an overwhelming flood of information into a treasure trove of discoveries. What's truly exciting is how these advancements are converging. Telescopes equipped with cutting-edge sensors, combined with advanced computational techniques, are opening up entirely new ways to explore the cosmos. For example, the Vera C. Rubin Observatory, set to begin operations in the next few years, will map the entire southern sky in unprecedented detail, revealing millions of galaxies and potentially uncovering clues about dark matter and dark energy. Each of these missions brings us closer to answering some of the most profound questions in science. How did the universe begin? What is it made of? And where is it headed? The pace of discovery is accelerating, and with it, our ability to piece together the story of the cosmos. As we look ahead, it's clear that the future of cosmic time travel isn't just about looking back. It's about understanding our place in the grand tapestry of the universe. Every new technology, every mission, and every discovery brings us one step closer to unlocking the secrets written in the light of ancient stars, waiting to tell their stories across the vast expanse of time. There's something deeply human about looking up at the night sky and wondering what lies beyond. It's a question that has echoed through the ages, from the earliest stargazers to the scientists of today. The study of ancient light isn't just about collecting data or mapping the cosmos. It's a reflection of our innate curiosity, a drive to explore the unknown and make sense of our existence. Why are we here? Where did it all begin? These are the questions that have shaped civilizations, inspired myths, and fueled scientific discovery. When we peer into the depths of space, we're not just observing distant galaxies or ancient starlight. We're connecting with a story that began billions of years ago, a story that includes us. Every photon of light we detect from the far reaches of the universe carries a piece of that story, a snapshot of a moment long before Earth even existed. It's like holding a letter from the past, written in the language of light, and deciphering it gives us a glimpse into the origins of everything we know. This quest to understand ancient light is more than science, it's a journey of meaning. It reminds us that we're part of something much larger than ourselves, a universe that's vast, mysterious, and beautiful. The emotional weight of this realization is profound. It humbles us, yet it also inspires us to keep exploring, to keep asking questions. After all, curiosity is what pushes us forward, what drives us to build telescopes, launch probes, and dream of what lies beyond the stars. And it's not just about the answers we find, it's about the questions we dare to ask. Every discovery opens new doors, revealing possibilities we never imagined. The study of ancient light is a testament to humanity's unyielding spirit, our refusal to accept the unknown as unknowable. It's a reminder that the universe is full of wonders waiting to be uncovered, and that the journey of exploration is as important as the destination. The idea of cosmic time travel has long been a wellspring of inspiration for storytellers, weaving its way into the fabric of popular culture and sparking imaginations across the globe. Think about it. How many times have we seen a spaceship hurtling through the void, its crew witnessing the birth of stars or the echoes of long-dead galaxies? These stories, born from the science of ancient light, have shaped how we envision the universe and our place within it. Take, for example, iconic films like Interstellar or 2001, A Space Odyssey. These cinematic masterpieces didn't just entertain, they brought the mysteries of the cosmos to life, using the concept of time dilation and the vastness of space to explore profound questions about humanity, existence, and the nature of time itself. The light from distant stars, traveling billions of years to reach us, becomes a character in its own right, a silent witness to the unfolding drama of the universe. But it's not just movies. Literature has also embraced the allure of ancient light. Authors like Arthur C. Clarke and Carl Sagan have used the idea of cosmic time travel to craft narratives that blend hard science with philosophical wonder. In Contact, Sagan imagines a journey across the cosmos, guided by signals from civilizations long gone, reminding us that the light we see today is a message from the past. These stories challenge us to think beyond our immediate reality, to ponder what it means to exist in a universe where the past and present are so deeply intertwined. Even in art and music, the concept of ancient light has found expression. Visual artists create stunning depictions of galaxies and nebulae, capturing the ethereal beauty of light that has traveled eons to reach us. Musicians, too, have drawn inspiration from the cosmos, composing symphonies that echo the vastness and mystery of space. It's as if the light itself becomes a muse, inspiring creativity across every medium. What's fascinating is how these cultural works reflect our innate curiosity about the universe. They remind us that the light we see isn't just a scientific phenomenon, it's a bridge to the past, a way to connect with the history of the cosmos. Through stories, art, and music, we explore what it means to be part of something so much larger than ourselves, and in doing so, we bring the cosmos a little closer to home. As we peer deeper into the cosmos and uncover the ancient light that tells the story of our universe, an important question arises: what do we do with this knowledge? The ability to trace the history of the universe through cosmic time travel isn't just a scientific breakthrough, it's a profound responsibility. Imagine holding a key to understanding the very fabric of existence. With that power comes the need to ask ourselves how we should wield it and what ethical boundaries we must respect. One of the most pressing concerns is the potential misuse of this knowledge. If humanity gains the ability to observe or even interact with events from the distant past, could we inadvertently alter the course of history? Even the act of observation carries weight. In quantum mechanics, the observer effect suggests that simply watching a system can change its behavior. Now, scale that up to cosmic proportions. What if our very act of looking back in time disrupts the delicate balance of the universe? These are not just hypothetical questions, they're ethical dilemmas that demand careful consideration. Another layer to this conversation is the societal impact. Knowledge of the universe's history could unite us, offering a shared understanding of our origins and place in the cosmos. But it could also divide us, as differing interpretations or access to this knowledge create new power dynamics. Who gets to decide how this information is shared? Should it be freely available to all, or controlled to prevent misuse? These are questions that challenge not just scientists, but philosophers, policymakers, and every one of us. And then there's the question of our role as stewards of this knowledge. If we uncover truths about the universe that could reshape humanity's future, like the existence of other civilizations or the inevitability of cosmic events, how do we handle that? Do we share everything we learn, even if it might cause fear or unrest? Or do we filter what we reveal, balancing truth with the need to protect and guide society? These decisions aren't just about science, they're about morality, responsibility, and the kind of legacy we want to leave behind. At its core, cosmic time travel isn't just a journey through space and time. It's a journey into the very essence of what it means to be human. It forces us to confront our values, our limitations, and our potential. As we unlock the secrets of the universe, we must also unlock a deeper understanding of ourselves, ensuring that our pursuit of knowledge is guided not just by curiosity, but by compassion and wisdom. The universe may hold endless mysteries, but perhaps the greatest mystery of all is how we, as a species, will choose to navigate the ethical frontier we now face. When we look at the faint glow of ancient light, we're not just observing distant stars or galaxies, we're peering into the very story of the cosmos. But this journey goes beyond science. It touches something deeply human. What does it mean to uncover the universe's history? How does understanding where we came from shape who we are today? These are questions that have echoed through human thought for centuries, and now, the light from billions of years ago offers us a new way to explore them. Think about it. Every photon of ancient light carries a message from a time long before Earth even existed. It's like holding a letter from the past, written in a language we've only recently begun to decode. As we unravel these messages, we're not just learning about the universe, we're also learning about ourselves. The same processes that forged stars and galaxies also created the elements that make up our bodies, our planet, and everything around us. In a very real sense, we are stardust, shaped by the same cosmic forces that govern the vast expanse of space. This connection between the cosmos and our existence raises profound questions. If the universe has a history, does it also have a purpose? Are we merely accidental products of cosmic evolution, or is there something more to our place in the grand scheme of things? These aren't just scientific questions, they're deeply philosophical, inviting us to reflect on our role in the universe. The study of ancient light doesn't just tell us where we came from, it challenges us to think about where we're going. And yet, even as we grapple with these big ideas, there's a sense of awe that unites us. Whether you're a scientist analyzing data from a telescope or someone simply gazing up at the night sky, the realization that we're part of something so vast is humbling. It's a reminder that, for all our differences, we share a common origin in the stars. The light that reaches us from across the cosmos isn't just a scientific tool, it's a bridge connecting us to the universe and to each other. Imagine a child gazing up at the night sky, their eyes wide with wonder as they try to grasp the idea that the light from distant stars has traveled for millions, even billions, of years to reach us. That moment of awe, that spark of curiosity, is where the next generation of cosmic explorers begins. The study of ancient light isn't just about unlocking the secrets of the universe. It's about inspiring young minds to dream big and ask the questions that push humanity forward. When we share the story of cosmic time travel, we're not just teaching science, we're igniting imagination. Think about it. Every photon of light from a faraway galaxy carries a piece of history, a snapshot of the universe as it was eons ago. For a young person, that's not just a fact, it's a gateway to wonder. It's the realization that they're part of something vast, something timeless, and that realization can be transformative. But inspiring future explorers isn't just about showing them the stars, it's about making the journey relatable. Take, for example, the James Webb Space Telescope. It's not just a marvel of engineering, it's a tool that lets us peer into the universe's past. When we explain how it works, we're not just sharing technology, we're showing how curiosity and collaboration can lead to groundbreaking discoveries. Stories like these help young people see themselves as part of the scientific adventure, whether they're future astronomers, engineers, or simply curious thinkers. What's more, cosmic time travel is a reminder that science is for everyone. It doesn't matter where you come from or what resources you have. Anyone can look up at the night sky and wonder. That's why programs that bring astronomy and space science to schools, communities, and underrepresented groups are so vital. They ensure that the next generation of explorers reflects the diversity of humanity itself, bringing fresh perspectives and ideas to the table. So, how do we keep that spark alive? By making the cosmos accessible. Whether it's through hands-on activities, engaging storytelling, or simply taking the time to answer a child's questions about the stars, we can nurture that sense of wonder. After all, the kids who grow up marveling at ancient light today might be the ones who build the telescopes of tomorrow, or even discover the next great cosmic mystery. The beauty of cosmic time travel is that it reminds us all to look beyond our immediate world and dream of what's possible. And when we share that vision with young minds, we're not just teaching them about the universe, we're helping them see their place within it. That's the true power of ancient light. It doesn't just reveal the past, it lights the way to the future. As we wrap up this cosmic adventure, it's impossible not to marvel at the incredible journey light has taken us on. From the tiniest flickers of ancient starlight to the vast, swirling galaxies that stretch across the universe, light has been our guide, our storyteller, and our time machine. It's more than just waves and particles. It's a living archive of the cosmos, carrying secrets billions of years old. Think about it. Every beam of light we observe is a snapshot of the universe's past, a message from a time long before humanity even existed. This isn't just a story about science, it's a story about us. Our curiosity, our drive to explore, and our relentless pursuit of understanding have brought us to this point. We've decoded the whispers of the Big Bang, traced the birth of galaxies, and even begun to unravel the mysteries of dark matter and dark energy. And yet, with every discovery, we find ourselves staring into an even deeper abyss of questions. That's the beauty of it. The universe is infinite, and so is our quest to understand it. So, what's next? As technology advances and our tools grow sharper, who knows what new chapters of the universe's history we'll uncover? The story of light is far from over, and neither is our journey. Thank you for joining us as we explored the wonders of cosmic time travel. If this journey sparked your curiosity, let us know in the comments below. And if you'd like to keep exploring the cosmos with us, hit that like button, subscribe, and share this video with fellow stargazers. Until next time, keep your eyes on the stars and your mind open to the endless possibilities of the universe. See you out there.